Good morning, everybody. I hope you're doing well for this last day of this JSI conference. On behalf of the organization committee, I'm glad to introduce our first speaker, keynote speaker of this morning, Diarra Fall. From my point of view, Diarra Fall is a perfect JSI profile. She started in theoretical mathematics. Then she continued she moved to data processing, and in particular, she worked in CEA. CEA is French Atomic Energy Commission. And then she moved to statistics and numerical analysis. And now she's affiliated to the University of Orléans. She's a leader of two projects called Pianica and Cournier, whose aim is to understand brain activities. So today she will talk about mathematics and medicine, and I'm glad to hear what she has to say to us. The stage is yours, please.
Thank you. Okay, thank you, Barbara. Thank you, everybody, for being here. I would like first to thank the organizer for inviting me. For me, it's a great pleasure and a big honor to be here. So thank you for this kind invitation, and I hope you enjoy this nice conference. So as Barbara said, I am very interested in the application of mathematics, particularly for medical imaging. So I'm going to talk about that. So here is the outline of my talk. I don't know if everyone here in this room is familiar with Bayesian parametric and non-parametric. So I'm first going to make an introduction to introduce these terms. After that, I will, After that, I will present a study, so research I made with some neurologists at Orléans Hospital about Bayesian non-parametric and Bayesian parametric. After that, I will move to image reconstruction before, and so I will end with the conclusion and perspective of this job. Okay. So let me now move to the introduction about parametric versus non-parametric. To me, a parametric model is a model in which the number of parameters is fixed or bounded by a constant with respect to the sample size. Okay? So this is the definition of a parametric model. And in a non-parametric model, the number of parameters is not fixed. So it can dynamically grow with the data and their structure. Alternatively, we say that a model is non-parametric if the parameter is infinite dimensional. So typically, when we have a function, for example, a probability density function, a cumulative density function, or a regression function. So when you have a function as a parameter, your model is non-parametric. Okay? So in a parametric model, the number of parameters is fixed. And in a non-parametric model, the number of parameters can be infinite dimensional. So I have two examples. The first is a regression model. So we have observation x and y, x from x1 to xn, and y from y1 to yn. And we are interested in the relation between y and x. So in a parametric framework, we model this as follows. So we have y equals f of x parameterized by beta. So our parameter is here the vector beta, so of size p plus 1. And here, the variance of the error. So our parameter is just a vector, okay? So for example, if you have a linear regression, your parameter are here the regression coefficient, beta 0 and beta 1, okay? Or for example, a polynomial regression. In all of these cases, your parameter is of finite dimension. Okay. So, oops, sorry. In a non-parametric framework, the parameter is the function f itself. Okay. So in a parametric framework, here the parameter is the vector beta. In a non-parametric framework, the parameter is the function f itself. So the only assumption we put on f is some assumption of smoothness. Okay. The second example is the density estimation problem. So we have observation x from x1 to xn that are IID with some cumulative distribution capital F. And we want to estimate the density. So that is the derivative of the cumulative F. In a parametric framework, we can assume that F belongs to some parametric family, typically a Gaussian family, that is parameterized by the mean and the covariance matrix, for example. Or you can, for example, assume that your density is a finite mixture model. So in this case, your parameters are the weights, the parameters here, and the number of components. Okay? But you can see in these two cases, your parameter is of finite dimension. In the non-parametric framework, you just say that so your parameter is your density f, and it is a probability density function, okay, with the assumption that it is a probability density function, so it's sum to 1, it is positive, etc. Okay? Or alternatively, you can consider an infinite mixture model. Okay? So in this case, you are non-parametric. And the last example is the clustering problem, in which you are interested in partitioning objects into clusters. So in a parametric framework, the number of clusters is finite. In a non-parametric framework, this number is potentially infinite. Okay, so I hope now you are familiar with this notion of parametric and non-parametric. So I think it is interesting to define them. Let me now move to the Bayesian, because I'm going to talk about Bayesian non-parametric. So I first want to introduce parametric versus non-parametric and Bayesian. So a Bayesian model assumes that the parameter is a random quantity. Okay. So what does it mean? So again, the example of the density estimation. We have data x1 from xn, and we want to estimate the density. I consider here just a parametric framework. We have the parameter theta. When we are Bayesian, we need 3 ingredients. The first is a prior. Okay? We put a prior over the parameter. So here we put a prior over theta. We put a prior over theta, that is pi. We consider the likelihood, the joint distribution of the data, that is seen as a function of the parameter. And we compute the posterior using a Bayes theorem. Okay? So to compute the posterior, you need the prior here and the likelihood. So, and this term. So if you have this posterior, or an estimate of this posterior, you can compute as an estimate of theta. You can consider the posterior mean. That is the optimal estimator with respect to quadratic loss function, or the maximum a posteriori. That is the optimal estimator with respect to Bregman divergence. So in this nice paper by Marcelo Pereira, so he considers some aspect of differential geometry to show that. Or, for example, you can consider another estimator like posterior median. Okay? So being Bayesian, all the inference about the parameter lies on the posterior distribution. Okay, now what is a Bayesian non-parametric model? It's a Bayesian model on an infinite dimensional parameter. Okay, so you have again this example. So in a problem of a density estimation, we are interested in a density. So the parameter space is the set of continuous probability distribution. In a regression problem, the parameter space is the set of smooth functions. And in a clustering problem, that is the set of the partition functions. So we need to put prior on function. So we say that here f is distributed according to calligraphical f, when this calligraphical f is a stochastic process. So a stochastic process is just a distribution on functional spaces whose sample paths are functioned. So the stochastic processes form the core of many Bayesian non-parametric models. Okay? We need to put prior on function, so we need stochastic processes. You have here some example of stochastic processes. The Gaussian process, whose realization are continuous function. The Dirichlet process, one of my favorite Bayesian non-parametric model. But the realization are discrete probability measures, so they do not admit density. We can consider Dirichlet process mixture. So if you are modeling, for example, a density. And today I'm going to talk about polyatry. So it's also one of my favorite Bayesian non-parametric models. What is interesting is in polyatry is that you can parameterize your tree to, so if you want to have discrete or continuous probability measures. Okay. And now I'm going to talk about this, this study. So that is a Bayesian non-parametric test for the study of language arrays in stroke patients. So that's research I have made with some neurologists at Orléans Hospital. Okay. So let me now just introduce the context of this work. I'm going to talk about language pathology. So it is worth mentioning that this language pathology is a common and serious defect after stroke. According to epidemiological studies, nearly 25 to 30% of stroke patients develop such a defect. Okay? So the aim of this work was to identify the brain areas that are involved in this trouble. So what I am going to call the language areas. So to do this, there is a reference method in the medical literature that is called voxel-based lesion symptom mapping. The procedure is as follows. There are two steps. In the first step, so we have n acute ischemic stroke patients. In the first step, they undergo imaging, so that is typically MRI. So we have here, let me show you here. We have here the 3D T1 image that is used to identify the lesions, and the lesions are delineated here on the diffusion image. Okay? And here, for example, you have an MRI with a lesion that is here. Okay? And since all the patients do not have the same brain, so these images are normalized with respect to an ideal brain. And we obtain what we call a mask. A mask here is just a binary image. Okay? For example, so we have just here in white the lesion. Okay? So this is the first step. This is the first step. And so that's what I mentioned. So we have the lesion maps of each of the patients. In the second step, the patients are evaluated with the language screening test. That is a neurological test. In this test, there are two subscores. The first is an expression score, and the other one is a receptive score. So the total sum of the score is considered, and the maximum is 15. And if the score is less than 15, the patient is ranked as symptomatic. So what is aphasic here? So why? In the last test, there are these two parts. In the first part here, for example, the patient must give a name to some object. For example, here, he must say that this is a pencil, this is a television, knife, etc. So this is the expression part. And in the receptive part, he must designate here, for example, the object. So to designate here the tomato, or for example, perform some task like touching the ground, etc. Okay? So if the patient fails in this test, it means that he is aphasic. So we have these two things, the image of patients' lesions and the score to the last test. So using this, statistical tests are performed voxel by voxel, okay? And the object is to identify the voxel which controls the language, so what we call the language area. So the aim of this work with Dr. Ozu was first to confirm or refute the implication of the classical language areas using this test, the last test. And so what he asked me is to know if it is possible to reduce the number of patients that are included in his study using a different statistical approach. Okay? Because it was difficult to obtain these patients. So he asked me if it is possible to develop a new method to this aim. Okay, so let me begin with some notation. Let y from y1 to yn denote the last score of n patients, and g is the number of voxels. So in each voxel j, and each patient n, I can define a binary variable, z and j, that is equals to 1 if voxel j in patient number n is lesion, and 0 otherwise. And yn is the score to the last test. So that belongs to between 0 and 14 if patient n is aphasic, and that is 15 otherwise. So in each voxel j, we can partition the patients into two groups, group 1 and group 2, with 1 denoting the patients who have this voxel lesion. So here, y1j is the set of score of patients whose voxel number j is lesion, and nyj is the cardinality of this set, and the same for y2j. So this is a test problem. Why? Because we are interested just in whether the two groups, we have two groups, in whether these two groups are different or not. So I can write this as then y1j, so this vector, we have a set of samples that is distributed according to f1, and the same for y2j, distributed according to f2, where these two functions are unknown. And we consider in each voxel just these two competing hypotheses. H0, these two distributions are equals, versus they are not. This is a two-sample comparison problem. So significant voxels such that H0 is rejected are considered as belonging to language area. So this is a two-sample comparison problem that is performed in the medical literature using student t-test. But you may know, I hope, that if you use a student t-test, you are assuming some normality. So you have to check if this normality is met or not. Or, for example, nij's that are big enough using the central limit theorem. Okay? Alternatively, you can use a non-parametric test, a frequentist non-parametric test, like Mann-Whitney or Kolmogorov-Simeonov. And I propose to use a Bayesian non-parametric test. So just before mentioning, just let me mention this. The difference between a frequentist and a Bayesian hypothesis testing. So when you perform a frequentist test, you do not assign probability to your hypothesis, but rather to the statistic of the test. Okay, so the statistic of the test is your random variable. So p-values are often mistaken for probabilities of hypotheses. Okay? A p-value is not a probability of a hypothesis. So a p-value measures the agreements of your data with the model that is postulated by H0, but not the probability of H0. Okay? Because you are frequentist, you are not assigning a probability to your hypothesis. In contrast, when you perform a Bayesian hypothesis testings, so your hypotheses are assigned prior distribution. So And you can just choose the largest hypothesis with the largest posterior probability. So it is conceptually straightforward to understand and to explain. I think there are a lot of people who do not really understand what is a p-value. So, so here is the Bayesian hypothesis testing. So we consider these two hypotheses, H0 and H1. Okay? And we want to assign prior probability to this hypothesis. To do this, we consider a prior density, pi of theta. And we can compute the prior of H0 and H1. That is just given as follows. Okay? So this prior is pi 0, and the prior of H1 is pi 1. Okay? So you have these two prior probabilities. And you can judge your two hypotheses using what is called the prior odds ratio. That is just pi 0 over pi 1. So this is the first step. Okay? In the second step, so you know when you are Bayesian, once you observe your data, you update your belief about the parameter using the posterior distribution. So you have this posterior density. And you can compute the posterior of each of these of the hypotheses. So posterior of H0 and those of H1. So this is P0 and P1. And so you also update your hypothesis using now the posterior odds ratio, that is P0 over P1. And we use what we call the bias factor, that is just the ratio of the posterior odds to the prior odds. So that is given by this expression. So the bias factor is a measure of the evidence that is provided by the data in support of H0. And we also have this link between the posterior probability and the bias factor. Okay. And now, so the test I propose is based on a Bayesian non-parametric. So as I mentioned, because I am Bayesian, I put prior on the unknown, okay? And my unknown, I have R function, okay? So I have two setups of sample. The one is distributed according to F1 and the other to F2. So I put prior on this function, and I am non-parametric, okay? And the prior are polyatries. Okay, now I'm going to define after what is a polyatry. But why? Just to motivate this choice. So I have already mentioned that when performing a Bayesian test, allow to have a clear interpretability of what you are doing as compared with p-value. And also something that is very important. So a Bayesian approach is not based on asymptotics, so it allows to handle small sample size. As I mentioned, so the neurologist asked me if it is possible to reduce the number of patients. So that's why also I consider this Bayesian approach. And a non-parametric test, because the polyatry allows to center the probability distribution, I'm going to mention this after, at a given parametric model. So this allows to embed this parametric model in a larger non-parametric one. Okay, so what is a polyatry? Polyatry are specific distribution on probability measures. So they are natural candidates for prior on probability measures. You have this nice paper, so that are very technical papers, but you have this nice paper about polyatries. This paper by Dobbins, Friedman, Fabius, and Kraft. Okay? And the name polyatry appears here in this paper by Moldin, Suders, and Williams. And if you want to have a review and basic properties of polyatry, you have the nice papers by Lavin here. Okay, but so they are very technical. So I'm going just to define it by construction. What is a polyatry? To do this, you need a sequence of partition. So here I consider, for example, the dyadic partition of the unit interval. So what does it mean? Let me just show you this here. Here at level 1 of the tree, you have the unit interval. at level 0. Sorry, at level 1, so you have these two dyadic partition. So the first is 0, 1 half, 1 half, 1. At level 2, you have these 4. So 0, 1, 4, 1 half, 1, 4, yeah, and so on, okay? So this is called the dyadic partition of the unit interval. So you need this partition, so here, just this dyadic partition. Level 0, level 1, level 2, and so on, okay? You have to do it infinitely, so in theory. And so here I consider just the dyadic partition. You have your partition, and you want to construct a random probability measure. To do this, you just have to define sequentially the probabilities. You have to assign a probability to each of the elements of your partition. Okay, you can do this as follows. Here. For example, here, you consider random variable here, W0, and W1, that is 1 minus W0. Okay? And so in a polyhedry, these random variables are distributed according to a beta distribution. Okay? So you sample here a random variable W0 and a W1, and the f of B0 is just W0, and f of B1 is W1. Here, to move from here to here, you also have to sample W00 and W01, that is 1 minus W0. And the f of this B00 is just W00 times W0. Okay? So yeah, that's what this means. So how to construct a polyhedry on this unit interval. So that's what is defined here. So it seems complicated, but it is not. Okay? So you have to define this. So see, this is just what I explained. Okay? Then you have assigned a mass to each of the elements of the partition. And it is called a tail-free process. It means that these variables are mutually independent, this random variable. Okay, so doing this, you have defined a random partition. So this is what I mentioned before. In a polyhedry, your random variables are independent beta random variables. Okay, and this is what I explained here: how to construct the probability for each of the elements of the partition. Okay. So we have to choose the parameter. So these are the parameters for the beta variables. Okay, and we have to choose these parameters. So, and these parameters define the kind of measure you obtain. So if you choose, for example, the parameters to be equal at the left or at the right-hand side of the tree, so that's what this means. So you have the expectation of the beta variable that is 1/2. And if you choose your parameters to depend on the level of the tree, so that's what this means. And so you have this beta variable. And the more these beta variables are concentrated around their expectation, the more regular the random measure is. For example, you have this Kraft condition. If mu is a Lebesgue measure on X, for example, the unit interval, you have this Kraft condition. So if this condition is met, your polyhedry generate random probability measures that admit density with respect to Lebesgue measure. So you have something that is almost solely continuous. So that's what this means. And in the particular case I have assumed, so if you have this condition, so this condition that is met, for example, for this parameterization of the tree, so you have something that admits density with respect to Lebesgue measure. And here is you have a special case when you have a discrete measure. So if you parameterize your polyhedry in this way, the polyhedry is a Dirichlet process. So I mentioned that the Dirichlet process is a discrete probability measure. Okay, so you recover the Dirichlet process. Okay, so I hope it is not too technical. So just a last nice property of the polyhedry is its conjugacy property. So what is important when we are doing Bayesian? What does it mean? If you have x1, xn that are IID f, okay, a random probability measure, and F is distributed according to a polyarity. The posterior distribution, that is F given X, is also a polyarity with updated parameters. Okay, so that's something, this property is important, for example, for making inference on polyarties. Okay, so I mentioned that we have to choose the parameters of the beta distribution, and we have also to choose the partition of the space. So you have these two elements for defining your polyarity. So in practice, it can be difficult to elicit this partition. So what we can do is to center the polyarity around a chosen parametric distribution, F0. So we see the F0. And take the partitioning subset to coincide with the quantiles of F0. So for example here, you can choose your partition as follows. So if 0 is just a parametric distribution, it can be, for example, the Gaussian distribution. And doing this, so we show that, so we have a dual notation where the partitioning space is replaced by F0. And so if F is a random measure generated by a polyarity, and you choose F0 as follows, so your partition element as follows, the expectation of the random measure is just F0. Okay. And, okay, now let me come back to the test formulation. So I have these two samples, just to recall. I have to compare these two distributions. So I have two samples, x1 from xn1 and y here. And I want to test that these distributions are equal versus they are not. Okay? So Z is the combined sample. Under H0, so under H0, these two distributions are equal. So both samples come from a common distribution. So that is here, if not. Under the alternative hypothesis, I have this. So X that is distributed according to F1, Y according to F2, and these two distributions are different. Okay? So I have three random probability measures, F1, F2, and F0. Okay? And I put a prior on this three distribution by considering a polyarity. Okay? And to choose between these two hypotheses, a Bayesian test evaluates what I mentioned before, the bias factor. So the bias factor is given by this term. Okay? So here you have the prior probabilities of the hypothesis. In the test I consider, so I assign equal priors to H0 and H1. And the bias factor is just given by the ratio of the posterior odds. And that is given by this term. And one shows that the bias factor is given, so in the test I consider, the bias factor is given by this product of gamma. It just means that the bias factor has an analytic formula for the test I consider. So that is something that is very important in practice, to have an explicit formula. Okay. Okay, so now show you the application to real data. So the data are collected from 58 patients at Orléans Hospital. We have this patient who all suffered a single stroke, single left hemispheric stroke in the acute phase. And so the mean age of the patient is 19, and the max is 91. And you have here the standard deviation. So we have the last score and a binary lesion maps of each patient. That's what I mentioned before. And we are going to compare the proposed Bayesian non-parametric test with this frequentist test. The first is the student t-test, because that's the reference test in the medical studies. And the two frequentist non-parametric tests that are Mann-Whitney and Kolmogorov-Smirnov. So the significance level for frequentist test is here, 5%. And the number of analyzed voxel is more than 7 million. And here you have the parameterization of the polyarity I have proposed. And you have this result, okay? So for in each row, you have each of the tests. So this is the new test, Bayesian non-parametric, Bayesian non-parametric using polyatry. That's what it means. And the frequentist test, okay? So we first look at the results for 58 patients. Okay. So we have here different view of the brain. You may have a look here to this column. We must have two separated regions here, here and here. Okay. The first, so there are the language areas. The first is the Wernicke area, and the other is Broca area. So the neurologist said, not me. You have two regions, so you must have two separated regions. So with 58 patients, all the tests recover more or less these two regions. Okay. So if you look at what happened if you reduce the number of patients, if you consider 34 patients, we have this. Okay. So let me just explain. I think it is better to use these results. What happened? Okay. So you have here the tree test and the Bayesian non-parametric, and here's the number of patients. Okay. With 58 patients, we have this. So this is the number of significant voxels. So the number of voxels belonging to language areas. Okay. So with 58 patients, that's what I mentioned. All the methods locate more or less the classical language areas. So Broca and Wernicke's areas. Yeah, so this region is what I mean. The one is involved in the production of speech, and the other one in the receptive speech. Okay, with 58 patients, so other method locates these regions. So what happened with 34? So you can see it here. With 34 patients, only the proposed Bayesian non-parametric test produced stable regions. Okay. The frequentist test here failed in recovering the total area, so you can see it here. So the total Wernicke areas for t-test and Mann-Whitney, and both areas for Kolmogorov-Smirnov. Okay. So when we reduce the number of patients, so this method failed in recovering these two areas. So just to say that it was a good idea to consider a Bayesian non-parametric test. Okay, so just to conclude this part of this work, by developing a new Bayesian non-parametric test, this allowed to reduce the sample size, and we have also validated the last test from a statistical point of view. What happened here is that all the computing methods, so the Bayesian non-parametric and the other method, analyze a voxel independently of its neighbor. Okay, you just to look at what happened in a voxel, and so to the other voxel, and there is no dependence between this voxel, and so it is intuitive that if a voxel belongs to the language area, so it is likely that its neighbor also belongs to the language area. Okay. And so we think that a more realistic model should include these special interactions among neighboring voxels. Okay, so, and that's what is performed here. In this second study, with, so that is a research with Nicolas Daubijon. That is a Bayesian estimation formulation to voxel-based lesion symptom mapping. So in this second study, what we are going to do is a Bayesian estimation, not a Bayesian test. So I'm going to explain it. So we have proposed a second approach that is rather different from the first one. Okay, so we say that, so we think after that it was interesting to consider a more realistic spatial model that includes this spatial interaction among voxels. And to do this, the task is formulated as a statistical estimation problem rather than a testing procedure. Okay? What we are going to do, we are going to estimate the language area directly from the data without resorting to any test, any statistical test. To do this, so this estimation problem is cast in a Bayesian framework, but now we are going to be parametric. So, okay. So just some notation. We define an observable binary variable. So this is going to be our variable of interest. So this is just a binary variable that indicates voxel responsibility. So this binary variable is equal to 1 if voxel j belongs to the language area and 0 otherwise. Okay, we want to determine this map. And since in the last test, that's what I mentioned before, all the patients with a total score that is less than 15 are ranked as aphasic. So we can just threshold the score. So to do this, we introduce diagnosis variable by yn that is given as follows. So it is 1 if individual n is aphasic and 0 otherwise. Okay? And we have this. Okay, so we have this Z1, Z and J that equals to 1 if voxel J in patient N is lesion and 0 otherwise. So these variables are Bernoulli distributed, and we consider this model. So we have this likelihood. So here, Z and J, given that voxel J does not belong to language area, we have just a Bernoulli with parameter theta. And here, this means that voxel J belongs to language area and the patient is aphasic. And the same here for non-aphasic patients. So you have these probabilities. Theta, that is the probability across all subjects that a voxel outside the language area is lesion. And theta 1, that is the probability for lesion probability in the language area for symptomatic patient, and theta 0 the same for non-symptomatic patients. So we have these three probability of lesion, and now the set of unknown parameters is here, omega, that's what I say, it are parameters of interest. It is the card of language areas. So we have this, so this is a vector from omega 1 to omega j. I call that j is the number of voxels. So this is our parameter of interest, and this probability lesion. So these three probability lesion. So these are our parameters, and we put prior on these parameters. The prior as follows. For lesion probabilities, we just consider beta distribution, okay? And the parameter of interest to omega, I recall, the language areas we want to recover. So we want to incorporate some dependence. So that's what I mentioned here. So to introduce this dependence, this special correlation between neighboring voxel, we consider the Ising model. So the Ising model is given as follows. So it's just the probability of a voxel given the neighborhood is given by this. When this term, this term is the set of neighboring voxel, and this term promotes spatial regularization. So you have this parameter, the Ising field parameter, that is the beta I'm going to talk about. So we can just write the prior for omega as follows. So it is given by this term. And the parameter beta, the Ising field parameter, control the amount of spatial correlation that is introduced by the Markov random field. And so its value, the value of this beta, determines the level of spatial homogeneity between voxels. So if you have a value close to 0, this implies that your voxels are independent. So we'll consider values of beta that are greater than 0. And so it is well known that for Ising model, this normalizing constant is problematic. But it is not problematic if beta is known. Okay, so in this work, this value, the value of beta, will be fixed and adjusted beforehand. So we don't have to deal with this partition function. And given our prior, inference can be done easily using a Gibbs sampler. The full conditional distribution of the probability of lesion are also beta distribution with updated parameters. And the posterior distribution of the Markov random field is also a Markov random field. So we have conjugacy properties that simplify the inference. And this second method we propose is also compared with the four previous methods, the student t-test, the Mann-Whitney and Kolmogorov-Smirnov, and the Bayesian non-parametric I have proposed before. So you have here the results. Yeah, before the results. So the parameters have been chosen as follows. So this means this parameterization of the beta distribution, it's just a Jeffreys prior. So we have no idea, and we don't want to favor any value of the parameter. So we choose something that is nearly uniform. And for the Gibbs sampler, you may notice that the algorithm converges very quickly. So we don't need a lot of iteration. And we obtain this estimate of the probability of lesion. So that is in accordance in what we expected by the neurologist. And we estimate the parameter of interest using this, so the marginal posterior mode. And we obtain these results. So here, let me recall that here in this column, we have the two areas, Broca and Wernicke areas. Okay, so that's what is recovered here. And if you look at this last column, so you have this method, these three methods, the Bayesian non-parametric, and special is the new one. So I noticed, I hope you notice it, that we obtain something here that is not present here in the other method. So I was desperate. And I went to see the doctor, so the neurologist with who I work, and I said, so I don't understand what happened with my method, so I don't understand. I have something here that, so I thought that it was not normal to have this region. And so I said to him, I don't understand what happened. So I thought it would work, but it doesn't work, so I don't understand what happened. And he said to me, because you have discovered a new region, so a new region that is not Broca and Wernicke areas, that is a third region that is also included in language areas. So yeah, so that's what I mentioned here. So this new method allows to recover so both areas, but also a third region that is called supramarginal gyrus. So okay, so I was happy, and he also. So yeah, by reducing the number of patients, so yeah, see, this is what happened with the other test. So the Bayesian non-parametric test recovers the two areas. The frequentist test failed in recovering this area. So what happened in the previous, and the new method allows to recover both areas, but this third region. So I recall that the number of patients is reduced here. And oops. So just to conclude this part, so voxel-based lesion symptom mapping is something that is important for basic and translational human neuroscience research. And the classical VLSM studies require individual tests across hundreds of thousands of voxels. So, and another main limitation is what I mentioned, they require a large number of patients. So by proposing something new that is coherent, so this new method allows to outperform the state-of-the-art method when the sample size is reduced, that's what I mentioned, and also to discover a less well-known language area. Oh, madam, okay. Okay, just let me say something because I promised to talk about image reconstruction. Just for PET image reconstruction. So it will be very fast. So it was just to show that you can also apply this technique for image reconstruction, not only for image processing. Just what is PET? PET, positron emission tomography, is a functional medical imaging modality that is used in oncology, neurology, cardiology, and etc. To do this, a target molecule is injected into the patient's bloodstream. And this molecule is what is called a tracer, so that is a positron emitter radionuclide. An example in oncology is FDG, that is analog of glucose, and it allows to explore the possibility of cancer metastasis. So this radionuclide decays and emits what is called positron, and positron is anti-electron. So this positron annihilates with nearby electrons, and this produces the emission of 2 gamma photons moving in opposite direction. Okay? So that what is detected here in the detector surrounding the patients. And so the PET scanner is the ring of these individual detectors. So when 2 photons are detected here, so in the detector, in the same time, we say that a coincident event is recorded here in this virtual line, what is called a law. It is just the virtual line joining both detectors in coincidence. Okay, so the aim of PET reconstruction is from all the data that have been collected by the detectors here to reconstruct the image of the tracer distribution within the body. So this can be performed in a static framework or in a dynamic framework. Okay. So just to mention that PET image reconstruction is an inverse problem, in which we seek to obtain the estimate of the tracer density within the subject from the collected events. And it's very challenging. It poses inverse problem. You have here some of the problems. So the first one is because a radioactive substance is administered to the patient, so the total number of molecules is limited when compared to radiological X-ray, for example. And the other one is for the limited sensitivity of the camera. You have to deal with the physical and geometrical complexity of scanner, and so there are a lot of problems that happen. And the other one is that the image quality depends on the injected dose. So here you have different reconstruction, and you may, so this is the first one is a reconstruction under normal dose. Here you see what happens if the dose is divided by 10. And if the dose is divided by 100, okay? So the image quality is poor if you reduce the dose. And the aim of this work was to develop new image reconstruction method under a low dose. So, and also we wanted to characterize the associated uncertainty, because of course the uncertainty is big when you have a small number of events. To do this, so we have performed spatial and spatio-temporal PET reconstruction for cerebral and cardiac PET data. Oops. And what we do is that we view the image we want to reconstruct as a spatial or spatio-temporal probability density. Okay, so we are non-parametric, and because we are always Bayesian, we put a prior on this density. Okay, so I don't have time to explain it, but that's what we do. And the prior we consider as here Dirichlet process mixture, and in the spatial case, and in the spatio-temporal case, we have dependent Dirichlet process mixture and polyatry. So we have a lot of challenge to, for example, how to sample infinite dimensional parameters, how to deal with large data size, etc. And you have here, I'm going to show you a video just to explain what is it. Here is an example of cardiac data. And the tracer is injected in the patient arm. So here you have the arm of the patient here. And what happened? Yeah. And this is, in the first row, you have the conventional reconstruction. in this row, you have the Bayesian non-parametric we propose, and we are at the beginning of yeah. And yeah, so you can see the tracer here in the patient and after in the subsequent organs. So let me just explain what happened. Okay, so the tracer is indicated here in the patient arm. So you must see the tracer in the vein of the arm, and after in the vena cava, the right ventricle, etc. So what is important here is, for example, we must see here the tracer only in this part. So that is the vein of the arm. So this is not normal. What happened here with conventional reconstruction? This is not normal. Okay. So and you see that you have here. So I have a different frame. What happened here at this time? Okay. So you have this kind of things at this time, and also so you have what happened at different time, and also until the end of the exam, we have this kind of bias reconstruction that appears in the conventional method, and that does not appear here in the method we propose. Yeah, and the method we propose here, we are here in dose divided by 30. So, yeah, just to say that it works very well. Okay, so I'm going to conclude. Just if you want, I think I'm going just to do some motivation for being Bayesian. Why being Bayesian? So it allows to regularize your inverse problem by introducing a prior. And it is also a methodological paradigm to go beyond point estimation. So if you are fully Bayesian, so it allows to have, for example, variance, credible interval. And this is something very important, for example, for medical imaging to quantify the uncertainty. And why Bayesian non-parametric? So it allows to define and work with the model with large support. So this also sidesteps the model selection in your problem. It is an active research field and with new models and useful properties. So we have large variety of application of this Bayesian non-parametric. I also mentioned it very quickly, but you also need to have efficient sampling schemes for very large data sets. So that's something we have proposed here in this paper with Eric Barra. And you have a very large number of Bayesian non-parametric models. So I talk about the polyatry, Dirichlet process, but there are a lot of Bayesian non-parametric model you can use or you can develop if you want. And I don't know if, so just want to say a word about deep learning. What is the future for Bayesian inverse problem? I don't know. I have no answer to this question. But I think it is interesting to have a look to what happened in deep learning. I think that, yeah, this kind of work, I think that it's very interesting, for example, is to develop prior that are based on neural networks. Okay, so that is what is done here in this paper using plug and play ADMM. So your prior is defined by a neural network, and you can try to combine these things, and also being fully Bayesian for uncertainty quantification. So this is something I'm working on at this moment with one of my PhD students. So these are our preliminary results. So here we have deblurring problem. So this is the true image, our observation, and something we recover using a new method we are developing now. So that is really close to the true one. And also, in addition, we also have the standard deviation. So we can also characterize the uncertainty of the estimation. So, and it is also compared to end-to-end deep learning method, and we obtain a similar performance. And in addition, we also have this uncertainty quantification. So we are trying to develop it for large inverse problem. And here you have what happened, for example, in sorry. Thank you. You have what happened here in this problem. So we have this in painting problem. These are our observation, and this is what we recover, and also the uncertainty quantification. Thank you very much.
Thank you very much for this beautiful talk. Are there questions, comments in the audience? Yeah.
In your first example, it's absolutely unacceptable that the prior was not introducing the possibility of force areas.
Yeah.
So there is a problem with the knowledge at the beginning.
Yeah, I think so. I think so. So that's why we may do Bayesian, so to introduce this kind of information. Yeah.
Yeah, please. Can you help me pass the microphone, please?
Thank you.
Hi, thank you for the presentation. Short question, the polyatries, are there any relation to Cayley graphs? Because you have some, it looks like some multiplicative properties. Are there any connection?
Any connection to what? Sorry?
To Cayley graphs.
I don't know.
Cayley graphs are graphs that encrypt multiplication of groups, just as a visualization.
So I don't know. I don't know what is Cayley graphs.
Okay.
I'm sorry.
we can talk together.
Yeah.
Thank you for the talk. So at the, I think the first part, you showed that the method you've developed is more stable. But do you also have like some theoretical result that says that they are also theoretically more stable?
Yeah.
Okay, so it's in the paper. Okay.
Yeah, it is more
Okay.
stable, yeah.
Okay, good. Thank you.
Other questions? I have a remark for the audience more than for the speaker, actually. From my point of view, when I see this conjugacy property is something that is telling us that the space of your densities is stable by this step of using Bayesian. So is there a dynamical process behind? Like, can we understand it as a dynamical system on the probability space? I suppose this is the case. I don't know if someone knows more about this. So a geometrical point of view of what you're doing on this space of probability densities.
Yeah, maybe.
Probably there's something like this.
Yeah, I think so.
Are there other questions? So if not, please let us thank the speaker again.
So we have no parallel session. On the coffee break will be after the parallel session. So please try to change room as fast as you can.